Good morning, everyone. My name is Krzysztof Ciepielski. I'm a postdoctoral fellow at NCAR's Advanced Study Program, and today I'll be presenting a new approach to nonlinear data simulation that I refer to as Conjugate Transform Filtering. The main focus of my talk today will be to briefly outline the new theory and discuss how it can be used to estimate geophysical systems with varying degrees of nonlinearity. I would like to begin by expressing my gratitude to the session organizers for inviting me to give this talk, and I also want to thank my anchor mentors Jeff Anderson and Mocha Garanti, as well as Ian Grooms, Ricardo Baptista, Yusuf Marzouk, and Max Rangraba for useful discussions on this research so far. Let's set the scene for this presentation by briefly revisiting the Navier-Stokes equations, which are still our main tool for modeling geophysical flows. As you already know, the system of equations describes an incredibly rich spectrum of phenomena, but unfortunately is extremely difficult to solve and analyze mathematically. A lot of the complications are due to this nonlinear term here, which is known as nonlinear advection or convective acceleration, and is one of the main contributors to the development of turbulent motions. The nonlinear character of geophysical flows also poses challenges for data simulation and more broadly uncertainty quantification. In this figure from one of Mark Bouquet's papers, we see that even if our models are initialized with Gaussian uncertainties, the nonlinear dynamics quickly generate large deviations from Gaussianity, violating the typical assumptions of contemporary data simulation schemes. Another complication for data simulation methods is that nonlinearity and non-Gaussianity are not uniformly distributed across model variables. These histograms, which are generated from a 6-hour convection-allowing forecast, show that we have a nearly Gaussian distribution for temperature, a skewed unimodal distribution for precipitation, and a complex trimodal distribution for moisture. This distributional complexity is unfortunately not captured by operational data simulation methods. Despite their computational efficiency and stability, these methods like 3D-VAR, 4D-VAR, and ENKF rely entirely on Gaussian assumptions, which produce biases in the analyzed state. On the other hand, sequential Monte Carlo methods, such as the particle filter, do not make any distributional assumptions, but are difficult to use in high-dimensional settings. This reveals a clear gap in data simulation methodology and motivates the primary goal of this study, namely, to develop alternative data simulation methods which strike a better balance between accuracy, stability, and cost. To do so, we will make use of a subfield of machine learning known as invertible neural networks, which represent special neural network architectures where all functions are taken to be diffeomorphisms, which means that they're invertible, differentiable, and also have differentiable inverses. The key insight for us here is that invertible neural networks, alongside with the change of variables theorem, can be used to derive more flexible non-Gaussian distributions. The idea here is to start with a simple base distribution, such as the bivariate Gaussian in this example on the lower left, and then to apply a series of nonlinear diffeomorphisms, such as T1, T2, T3, and T4, to eventually arrive at a more complex distribution that more closely resembles the true distribution that our data may be coming from. So what I did here was to use this guiding principle to formulate a new state space model, which is needed for the derivation of our new data simulation approach. Without going into much of the notational details here, I just wanted to draw your attention to its special structure. In particular, we see that the highlighted terms in the brackets represent Gaussian random vectors, which are subsequently modified by the nonlinear diffeomorphisms f sub k and g sub k, which represent the state and observation functions. And just like this is similar to what we saw in the schematic from the previous slide. It turns out that we can write down the filtering distribution under this new state space model, which happens to be a Gaussian distribution that is pushed forward by the nonlinear state function at the current time step f sub k. The analytical tractability of this finding is quite encouraging, given the widespread perception in our community that exact filtering is not possible beyond the simplest Gaussian setting. However, there are two additional properties that I wanted to highlight here. First of all, if we take all state and observation functions f and g to be the identity transformation at all discrete times k, then the two recursion relationships at the bottom of this theorem coincide exactly with the standard Kalman filter recursions. So in other words, the Kalman filter is nothing more than a special case of this more general filtering theory. Another property that is closely related to Kalman filter is that at each filtering time, the prior is conjugate to the likelihood, regardless of how the observation functions g sub k are chosen. This special property gives rise to the name Conjugate Transform Filter, and in practice means that the analysis step of the Conjugate Transform Filter preserves the dynamical balances encoded in the prior state, which is crucial for accurate NWP predictions. So how does the Conjugate Transform Filter address the problem of having varying degrees of non-Gaussianity and nonlinearity in our state vector? Well, this depends on the nonlinear function f sub k, which can be chosen differently at each analysis time step t sub k according to the data simulation user. For instance, we can take f sub k to consist of dimension-wise exponential functions, which is equivalent to assuming that our prior has a multivariate log-normal distribution. And so in this case, our analysis update will be similar to the log-normal data simulation methods of Fletcher et al. However, the new approach gives us a little bit more flexibility here. Instead of using single univariate functions, we can actually stack multiple multivariate functions into a neural net and broaden the class of updating distributions. In theory, a smart neural network design should be able to approximate arbitrarily non-Gaussian distributions, making the Conjugate Transform Filter competitive to the benchmark particle filter. Just like the Kalman filter, however, a direct application of the Conjugate Transform Filter is not feasible, and we need to develop an ensemble approximation. The first step in doing so is to determine the parameters theta k of the nonlinear function f sub k, which, thanks to the conjugacy property of CTF, can be estimated directly from the prior ensemble. For instance, given these highly non-Gaussian forecast members, the optimal value of theta k would produce a density function which closely resembles and fits the empirical prior distribution. The second step is to approximate the highlighted Gaussian distribution, which is precisely the filtering distribution under a linear state space model. To obtain the desired Gaussian sample, therefore, we just need to transform our prior members to latent Gaussian space using our estimate of f sub k from step 1, and then just apply any of our favorite E and KF solvers. And finally, to get a posterior ensemble approximating the full filtering distribution, we just need to apply the estimated function f sub k from step 1 to the E and KF members from step 2. To validate this new data simulation approach, we'll consider a very simple numerical example whereby the prior members are sampled from this bivariate non-Gaussian distribution, which features a non-negative x1 component and a doubly bounded x2 component, a situation which is highly relevant to the type of challenges encountered in real geophysical models. We'll also suppose that we only observe the x1 component of the state, such that the measurement value is close to 0 and has a fairly small uncertainty, which is evidenced by the peak nature of the likelihood function. So on this next slide, we see that a simulation with the standard E and KF produces a highly biased analysis, which destroys the nonlinear relationship in the prior state and additionally creates a large number of ensemble members outside of the physical bounds, whereas application of the new eCTF method recovers the posterior exactly. To recap, today I introduced an exact nonlinear filtering theory, which generalizes the standard Kalman filter to arbitrarily non-Gaussian distributions. I also verified that an ensemble implementation of the new theory produces an unbiased analysis, which clearly outperforms the standard INCF for a challenging geophysical problem. While there are a lot of exciting topics and questions to explore with this new framework, my immediate next step would be to more systematically compare eCTF against ENKF and other nonlinear ensemble filters. Testing different neural network architectures in a hierarchy of toy dynamical models will be particularly illuminating and will likely shape the future directions of this research. Well, this is all I had for you today. Thanks so much for listening, and I'll be happy to take your questions later in the Q&A session.